All right. Good morning, everybody. So the last few weeks, we have been trying to improve on our housing sales price prediction for the city of Melbourne. And today we are going to continue that, and today will be the last day we work on that. So this is where we stopped off last time. We built a random forest model to improve on our decision tree. And finally, we got down to a mean absolute error of $182,000. So what we want to do this time is we want to try to improve on that by adding more columns. If you remember, the last time we had only picked certain columns, like the number of rooms, the number of bathrooms, parking spaces, etc. But think about, in many cases, you may not be able to go and look through every column and just arbitrarily pick. For homes, it might have been somewhat easy, but in many cases, if you have hundreds or thousands of columns, then you won't be able to go do that one by one. So in that case, what can we do, right? So that's what we're going to do today. And today's class might be, a little longer than the others because we do have quite a bit of stuff to cover. Okay. All right. So let's go ahead and get started right away. As usual, we are going to be including documentation all along the way and learning the syntax along the way. Okay. So we'll again bring in pandas. And we'll also learn. We are going to bring in the train test split. And then we are also going to bring in the metrics. We are going to bring in mean absolute error. That's what we have been using this whole time. All right. Bring in the data. Data, and we are going to be connecting back again to our Melbourne data set. This should be, after having done this for a while, this should start becoming almost muscle memory now for you. Okay, let's go ahead and select the target and features. We say y is dfmlb.look for all the rows, and we want to take price as the column. Actually, before we do that, let's see what this dfmlb looks like. And so we can get the column names. All right, so price is what we want. And this time for our X, we would like to use as many of the other columns as possible. So that's the main difference, okay? So let's select target and features. So Y is df look, all rows, price as the column. And now we want to take every other column and put it in X, right? So instead of listing out all the columns in X, we'd like to see how we can maybe just remove this price column and then use all the remaining, right? So let's go to pandas, say remove column. So there's something called data frame drop. So there's a dot drop function. So if you use the dot drop, so it says data frame dot drop, and then we need to give it the column name or names, multiple, and then it says axes equals 1. So axes equals 1, you'll see this in many places. Pandas has an interesting way of trying to figure out whether are you trying to drop columns or rows, right? Because this didn't say, so you could have done drop columns equals, but this axis equals 1 does come up a lot, so let's use that. So axis equals 1 means columns, and axis equals 0 means rows. because maybe if you had a row that had the same name, then you may want to be dropping rows, right? So let's go ahead and use this to drop that column. No burn, and then we're gonna drop just price, and axis is 1. Let's see what Y looks like. Yeah, that looks about right. And let's see what X looks like. Right, so it's got the columns, and see it skipped the price column. Okay, so all of that looks right. Now we'll go ahead and build our. Let's start by building our random forest model, but this time let's use all the columns. Okay, so let's say build random forest model, and again, because we're going to be doing this repeatedly, we have our steps, right? Define, fit, predict, and evaluate. So I'm going to encourage everybody to keep typing this, even though you can just copy and paste it, because it just makes it better for you in the long term. So, learn, and this was an ensemble. Yep, it was an ensemble for that was random forest regressor here. Okay, and we're going to do the define first. So model for which is I'm going to do the random forest for Melbourne, random forest regressor with the random state 1, because we're going to be comparing them. All right, so this was the define and the fit, and we didn't split our data, right? So let's go ahead and do that here. So X train, X test, Y train, Y test, train test split, X, Y, and then our test size of 0.2, the random state 1. Okay, so we've split that so that we could use it now. Fit X train, Y train. And then we are going to do our predict, but let's set that to Y best spread, and do model.predict test, and then our mean absolute error was comparing Y test and Y test. Right? So nothing new here. We are just running random forest for this data set, but now we are using all the columns, unlike last time where we had selected the columns. Okay, so what are we seeing here? Can't convert string to float. So there are some columns in X that are string that it needs to be numeric. So what that means is that the random forest model requires all of the columns to be numeric. So maybe we'll start with dropping all the columns that are string, and then using only the numeric columns, all the numeric columns. And then later on, let's also see how we can bring in some of the string columns. Okay, so by the way, we are going to be, since we're going to be running this same function quite a bit, the same model quite a bit, let's put it inside a function. We did this last time already, so I'm just gonna define, and let's call this get random forest mean absolute error, and we are going to be giving it X train, X test, Y train, test. Last time we also added the number of estimators, but this time that's not what we're testing, so we can go ahead and have that. Okay. Remember, in Python, everything is tabbed in. That's how it knows. We don't use so many brackets. All right, so we've got Okay. Sorry, this. Right. Creating our function, and now we want to create a function. Again, I do this so that we, as best practice, so that we don't confuse this with the actual data that we're passing in. Okay, so now let's do get random forest MAE with x train x test y train y test. Yep, should give us the same error. Okay, so now we want to drop the other string columns, okay, and then see if we could run the model with just the numeric columns, with all the numeric columns. But how do we do that? We don't want to go one by one and look at it manually. But before we do that, let me jump off here for a second. And then let's talk about the types of data. Okay. I mean, this is very basic stuff. But among the different types of data that are out there, we have. Let me just say. And I'm going to draw you out to some terminology because there's a lot of mixed terminology that you'll find. So among the different types of data, we would call one set. So we're going to call this numeric data, and then the other data I typically call it object data. So because this is non-numeric, right? So object data is non-numeric, but just because it is non-numeric doesn't mean it can still be used. So if it's numeric data, then within this you have discrete numbers and then you have continuous numbers, right? And on the non-numeric data, you're going to have what we call which is sometimes called object data, right? That means anything that's not numeric. But then some subset of that will be what we call categorical data. Okay, and non-categorical data. So this is data that is an object, but it's not a good candidate for machine learning, and we'll see that in a little bit. Okay, but then categorical data is objects that have a small number of unique values. So for example, an example of non-categorical data is address, right? So we are not exactly going to use address in any type of machine learning model unless you have many data points with the same address. Okay, so if we take all the non-numeric values and we look at the ones that have many unique values, we would throw them in here, right? And then we say we can't really use them because they're not going to anyway have a good impact on our model. But then the ones that have a small number of unique values, we're going to consider them as categorical. And then within categorical, of course, if it is, we've heard of this before. There's, you have nominal data. That means, things like so under nominal you might have binary. So you have things like 0, 1, true, false. You might have gender here, male, female, although that is more and more becoming non-binary. And then, or you might have, other nominal data is like color. So you might, red, blue, green, that kind of thing. So so these are called nominal. That means there's a small number, but there's no relationship between them, right? Basically, one is not, in any sequence compared to the other. Whereas in ordinal data, there is some kind of sequence. So, for example, if there's a, if you can rank something, right? This is stuff that can be ranked. So you might say whatever the letter grade, for example. Okay, letter grade would fall into this. You'll say A, B, C, D, and there is a meaning to it, right? A is better than B, which is better than C, which is better than D. And so anything that has some sort of ranking, then it will be called ordinal. But anyway, this is all just sometimes people will just call it numeric and categorical up here, but in the process of finding these columns, when you want the system to automatically find them, you want to know that just because it's not numeric doesn't mean it's going to be categorical, right? So the way you would use this is look at all of your columns. If you're, pick the numeric columns, use them, right? And if they're discrete or continuous, and if they're discrete, it kind of behaves somewhat like a categorical one, but you can still leave it as numeric, or they might be continuous. But then if it's non-numeric, then you would look for how unique are the values. If the number of unique values is too high, then we would put them into this non-categorical and not even use it or process it before we use it. If it does have a small unique number, then it goes under categorical, and then you may or may not specify whether it's nominal or ordinal unless you think it might make a difference. Okay, so this is a general way to think about the types of data. So we are going to start with numeric first, and then we are going to go and try to find some categorical values today. Okay, all right, so let's jump back into the model. So let's start with the numerical features, okay? Also, there's some people that use the term factors versus features, and we'll talk about the differences. People use them, interchangeably a lot, but there are differences between them. Okay, so let's select the numerical features. And like I said, we don't want to do them one by one. What we would like to do is, figure out what the type of each of the columns is, right? So if we go with pandas column type, there's something called D types, okay? That tells us what the column type is. So if we say X, which is, and then we say X.D types, for every column, it's telling us whether it's a float or object, right, or int. So we probably want all the ones that are int and float, right? Those would be our numerics. Okay, so, but we want to do that automatically. So let's put this into a loop. So for call in X columns, which gives us all the columns. We'd like to see, say, if X call, and we've already done for loops, so I'm not going over the syntax for that. So if X call dot D type is in this list, we want it, it's either int 64 or it is float 64, then we want, let's just go with print what it is. Okay, for now, print the call. Right. Okay, so it's giving us rooms, distance, postcode. So let's see, we got rooms, distance, postcode, bedroom, right? So it's picking them up properly. Well, but we want to now store this in a list, and it would be nice to kind of do this in one line. So I'm going to give you a little piece of code here that you might be able to use going forward, and it's a nifty way of doing this. So let's say that I want to call this calls num, and I want to make it okay, and I want to say that for all of this, go ahead and give me all the columns. Okay, so for call in X columns, if this is in this, and instead of printing it, give me the column that does that, and then put it in a list for me. Okay, that's what this code does. All right, so we basically did that, what we did before, but we want to put all of this into a list. So let's do that now, and then let's see what it looks like. There you go. So we got that in the form of a list. So this is a clean way of writing that, and then we're going to be sort of using this quite a bit, right? We have a loop, but we don't want to write out blocks of code just for that. All right, cool. So we now have our list of columns. So what we want to do next is now we want to redefine X as X train, X test, and all of that in terms of just these columns, right? So now let's go ahead and split the numeric features into train and test sets. So first we want to take for X as a subset, right? So let's do that also here. So let's call it X num now instead of X, and this is taking only the numeric columns. Okay, so if we say X num dot head now, okay, so now X num, which is X numeric, has only the numeric columns. Okay, and then so let's call it now X num train, X num test. Remember, we still have to split them into train and test sets because X num was done on the entire one. So train and Y test is train has split of X num and Y. We don't need to do anything for Y because Y is just one column and we know that it's numeric, right? So we're good to go there. Train size, sorry, test size. You can do train size also is 0.2 and random state. Okay, all right. So now we've split the columns or dropped the non-numeric ones. Okay, so now let's try and build a random forest model using all numeric features. Okay, no reason that should not work. So let's say that was get random forest MAE, but now instead of passing X train, I'm going to pass X num train, X num test. Now you see why we wrote that as a function also, so that we can call this Y train, Y test, right? Okay. All right, so now what are we getting? So this is all numeric values now, so we can't say anything about that. This is now saying that it has not a number or some null values basically. So let's look at the head here. Oh yeah, so even here, just within this, we have some non-numeric values. Okay, so basically this comes, we have missing values in our data set and we have to figure out what to do with missing values. But let's see how many missing values there are. Let's say pandas, let's say nan values. So let's see how do we find out if you have missing values? So you see this dot is NA tells us whether there are missing values or not. And so let's see how many missing values we have. So it's in the training set. So X num train dot is NA. That just says whether it's NA or not. But then let's sum them up by column. Right. So you see that the column car has 52 missing values. Building area has 5,000 missing values. So now the question is, what do we do with missing values, right? So let's come up with some approaches. So here, let's say dealing with missing values. So let's talk about that real quick, and then we'll jump back into the code. Okay? All right. So when we deal with missing values, let's say we have let's say we have something like this. We've got a bed in our table. Okay, we've got 1, 1, 2, 1, 3, 2, and we've got not a number value and a 2, right? Something like this. Okay, so one thing we can do is basically, just drop rows, right? So we can drop this row, this specific row here, because it has not a number value, and we can simply end up with something like this: 1, 1, 2, 1, 3, 2, and just call it a day, right? This is probably the quickest, simplest thing to do. But you also might lose a lot of information, right? Because what if there was only one missing value in this row and all the other values were filled up, right? You may be missing some information there, especially if you have a sparse matrix where you have missing values in every row, and if you try to drop, then you're going to lose a lot of information. But it's still a feasible thing to do. Okay. But then another thing that you could do is, of course, you can always drop columns, right? But we're hopefully not going to be dropping columns unless it has almost nothing. All right. So this is idea number one, which is dropping rows. Then, or a second approach here is by filling missing values. Okay. So you want to do imputation. So that's known as imputation. That means we are imputing values to be filled into this, right? So whenever we want to fill missing values, then also there are a couple of things we can do. We can fill it with, if we were to take, so we could do something like this. We could replace, so you got 1, 1, 2, 1, 3, 2, and this is what we want to replace. If we were to just, sometimes you can just replace it with some fixed value. So let's just say, whenever I don't know, I'm just going to replace it with a 0. Okay. So you can replace with a fixed value, whatever it is, maybe 0, if it makes sense, right? But then another thing that you can do is you can replace it with maybe the average, right, of the column. So if we say, all right, you know what, the average is a value of 2 here in this column, 6 divided by 3. So let's go ahead and just put a mean value of 2. So you can replace with some statistical value, maybe the mean. All right, and this is a very common thing to do because it doesn't put any overly strict assumptions on it. But then there's also sometimes, if you have specific kind of data, you can also do something called a forward fill or a back fill. So what you could do is, you could take whatever the previous value is and just put that in here. So you could either put 3, or if there was another value next, which was a 1, then that's called a backfill. That would just take that 1 and put it in here. Okay, so you might replace with a forward fill or a backward fill. And so forward fill and backward fill are mainly used in time series data, as it might make sense, right? So if you know that you have some trend information that is stored in your data, then you know that you might be in the absence of a data point, you might take the previous point because it's better than the average or better than some fixed value, right? So which of these options you pick really should depend on what type of data you are trying to fill. All right, so let's try some of those here in this data, and then we'll keep moving. All right, so let's first go with replace with missing data. Okay. So to know which columns have missing values, we just did this is NA, but maybe we want to come up with a list of columns, numeric columns that are null, that have null value. So we want car, building area, year built. So let's create this list and then drop them. Okay. So we can use code kind of like we did before, that one-liner piece of code. So we want to say that for call in x num chain dot columns, if x num chain call is NA, and we have to also specify, are we just going to do it if we're missing any one value, or if we're missing the entire row? So we're saying, if we're missing any one value, go ahead and drop it. Again, this is the most extreme case. All right, and then I want this as a list, so give it to me as a list. So now let's see if we are getting that as we want. Okay, good. So it's giving us car, building area, and year built, because those are the ones that have missing values. Actually, so in this case, we are actually dropping the column. We're not dropping the row. So it seems like these columns have many, and then the others have nothing. So that's why we are going to be dropping columns, not rows. But the same idea kind of works in terms of replacing them. Okay. So let's go ahead and drop that column. So we'll say x num train. These are numeric, but we have dropped the null values. That would be x num train, and then like we did before, we want to drop all the columns in this that are null, and we want to drop that entire column. So that's why axis equals 1, right? Like we said last time. Okay, and then let's do the same thing with the test. Right. Okay, so we've dropped the train and test values, and then now we are going to call the function again. So let's go ahead and copy that. But this time we are going to use the drop null columns. Right. Again, Y train and Y test nothing needs to be done because they nothing was dropped. Those columns are already numeric and good, right? Okay, so now it is trying to run, but it is having a problem with the shape of Y, of the column Y. So you might see this sometimes, that whenever you're trying to run some type of a model, and if you used Y dot in defining your column Y, if you used this method, then this is actually a data frame, right? It is still a data frame because it might only have one column, but it's still a data frame. So what this is saying is it doesn't like that, and it wants to change its shape. See, it was expecting a 1D array, and so this dot, the ravel function basically converts it from a data frame to a one-dimensional series. So let's do that here and then see if that fixes that. Okay. Let's see what's going on. see, we should, oh, oh yeah, because we need to convert the values to round. Okay. So sometimes we need NumPy for that. So let's see if it fixes that. No, that doesn't like that as well. So let's see how we can fix this. So again, the error was yes, PRD is not defined also. So we had this. That usually is mostly a warning. Yeah, so I think that this might have been, that's a warning. So maybe we can go back on that error. Let's go back to our function here. Just make sure that our function looks okay. Oh, here. So I had a little typo here. Okay. And let's reverse some of these changes. Hopefully those are just warnings and so we don't have to. Okay, so let's go do that. You clean this up. But that error was still the string. Then we did the numeric values. Okay. All right. Now we've had missing values. So now we fixed the missing values. And then we got our, okay, we dropped the null columns now. Now we are running this. Okay. Our function also needed to print, give us the return the MAE. Let's rerun that to get the MAE. So, all right, so we got now an error of 176, mean absolute error of 176, which is already better than what we had before of 182. Okay, so by the way, whenever we have errors like this, one of the reasons that in this class we actually want to come up with see these errors. We want to figure out why we have these errors, and then learn through experience, right? So as you go through your code, you will always run into errors also. And one quick way to find sometimes, so for example, if we wanted to really fix this one, we would have copied this, right? That's what I would usually do: copy this, paste it in, and then find Stack Overflow would definitely have a solution for this, right? Okay, so we have now a solution, but this is by completely just dropping the columns. But what if we don't want to drop the columns? See, car only had 52 missing values, right? But then we dropped that entire column just because of that. Building area maybe makes sense, but not car. So let's see if we can do some of the other ideas of not dropping the missing values. So let me just call this, let's say, approach 1, drop missing values. Okay, and then here, let's say, approach 2, impute missing values. Okay, right. So now what we would do is we'll try the filling the. By the way, a question always comes up. That there's something called here when you see this when you're working with missing data. You see that there's is NA and sometimes there's is null, right? You'll see is null is NA. So in Python and pandas, there's no difference. Okay, so you can either use is NA or is null. The reason that it's there, that you have both, is because pandas was originally brought in through both R and Python. And in R, you use more of one. In Python, Python, you use more of the other. So they just want to make sure that both are covered. Okay, but yeah, so all of this would have worked with is null as well. Okay, so now let's see if they show us what to do with inserting missing data here. All right, so filling missing out. So there's something called the fill NA. Okay, so you could do data frame dot fill NA, or in a specific column, right? You can fill NA with something exactly that you want. This was our one idea, right? Of replacing everything with a zero. See, it had nans here, and then it replaced it with zeros. So let's try that, and then and then there's a couple of other ways. There's something called method. So if you go to df.fillNA, what are the options there? There's an option called method, and you could either just give a value, right, like a zero or a mean or something, or you could do backfill, forward fill, and all of that. So we're gonna just quickly do some of those and then see if any of those help us. So let's say replace missing values with we'll just do it in code for now because we're somewhat short on time. Okay, so let's take our numeric values and okay, so instead of drop null, let me call it replace null now. And I'm going to take x num train and then do the fill NA. Okay, do the fill NA, and let's start with fill NA of just the value 0, and then do the same thing for test. Okay, so we can do that, and then let's get our random forest with now this replaced one. Okay. Right, so now we're filling the NA values with 0. All right, so just by filling them with 0, we got the error down from 176 to 167 further, right? So it's getting better. Let's replace it with something else, maybe with method equals forward fill. This is what I got from copying that other page code. Okay, this is with forward fill now. So we had 167 before. Now we got 172. So actually 0 was better. Let's just quickly try, the average. Let's try filling it with the average of the column. That's something that I've seen, work pretty well. Train mean. So mean gives you the mean of every column, right? So we're basically saying use that to fill the NA values. Okay. We had 167 with 0. Let's see if this one gets better. 166. Okay, so the mean gives us the best result. So from now on, what we want to do is, so going forward, let us replace all missing numeric values with the column mean. Okay, so let's say x train. I'm replacing the name of x train now, of all numeric columns with x num train rep null, which is what we just created, right? So that going forward, I'm going to use these imputed values. sets us up for. Okay, so now that we have done that, okay, so that's just a warning on trying to use .loc, but we're good. All right, so now let's, so this was all numeric features. So now let's look at some non-numeric features, okay? Let's see what we can do for those. So remember we said last time, we, in some cases we'll have, other columns, and we want to see, are there any that are categorical within that? And if those are, then, are they ordinal or nominal? And then we can use them, okay? So in order to even figure out which ones are non-numeric, we can use something just like we did before with finding out whether they were numeric, right? So we used this function here to figure out, to select the numeric features. So let's go ahead and do that. But this time we're going to look for object. Right? Those would be the, so let's call it calls bj for object. And now we want all the columns of D type object. If you remember, that's what they were called. Okay. So this is my calls object list. So remember, suburb, address, type, these are all objects, right? Now, remember I said that if we actually let's try running the model with just using all of these, okay, and then see what happens. So in order to use these are string values now. We need to convert string to numeric, right? Otherwise, it would throw an exception saying, I don't know what to do with these string values. That's why we even did the whole numeric section. That means we need to convert string to numeric. And I mean, you guys had already done some of this in your assignments, but that is what, so if we say, and does convert string to, actually not pandas, let's go with Python, which sklearn, because we're talking about in the context of machine learning, string to categorical. So this is called, there's just a pre-processing step in sklearn called label encoder. Okay, so some of you had already done this, but you really want to, kind of understand what it is trying to do. So label encoding does this. It takes the values that you have and then just assigns a numeric value to it, right? So for example, in this case, they've got Paris, Tokyo, and Amsterdam. Then, so from that, it assigns, it converted these to a numeric. So it probably converted, maybe alphabetical, probably converted Amsterdam to 0, Paris to 1, and Tokyo to 2, because these are the three different values, so 0, 1, and 2. And then later on, when it gets just Paris and Tokyo, you see that it converted to 1 to 2, right? So that's what it does. So we are going to use label encoding to convert those, the string values to numeric. Okay, and label encoding sometimes can get a little messy. But let's still go ahead and try that. So we got pre-processing. So it's within pre-processing, and it's called label encoder. So, and you call the fit function, and then you call the transform. Sometimes you can do fit and transform together. You see this fit and transform together. We can spend some time talking about fit and transform if necessary, but for now, let's go ahead and just use them as code. Okay. All right. So what we want is let's define, so from sklearn, that was pre-processing. Let's take the label encoder, and whenever we are encoding, we are going to be replacing the data frame, right? So let's call it XLE for label encoding. XLE train, and let's take X train and just make a copy of it so we don't lose it, and then XLE test, and go to X test copy. Now we can do some actions on XLE and not lose it. And I say label encoder is okay. We're going to initialize that, just like they had done here. See, they had initialized it here, and then they're using that name dot fit and then that name dot transform. So, and we want to do this for all the columns in this, right? In this. So let's do that. For call in calls obj, go ahead and do the fit and transform. So XLE train call. Let's take the label encoder and then do a fit. And so fit, maybe we'll talk about that here. So fit takes these values and assigns it some numeric one. Okay, it just does an assignment. So it says Amsterdam is 0, Paris is 1, and Tokyo is 2 because there's 3 unique values. Right? That's the fit. Transform then says, okay, I'm going to take those numeric values and apply it to this. And if you want to do both of them together, you can do fit and transform. So we can do fit and transform on the X train, on the X train for that column. Right, so we're taking X train, we are learning from it what the numeric value should be, and then we are applying it right away, and then we are putting it into this data frame. Okay, that's how you read that. And then we do the same thing for test. But remember, for when we are doing it on the test set, we don't want to learn from the test. We still want to learn from the train, right? So we learned, the fit was learned on the train. And then for test, we are just going to apply what we learned from the train, because the test set might not have all the unique values, right? That's the idea. So we're going to do only transform, and we're going to only transform from the test. Okay. All right. So we've done that. And so now that we've done the encoding, let's go ahead and actually run. So let's see if we got everything here. We got the encoder. We defined the encoder. We got XLE train and test. We went over the entire set here. And we're trying to do that. Okay, so what it is saying is that the count of the values, so basically it still has too many that are going on here. So remember in our notes we said that sometimes if you just because it's an object doesn't mean it's a good candidate to be a categorical feature. So we need to go ahead and look at how many non-unique ones, how many unique values do we have, and then pick only the ones which have a small number of unique values. Right? So let's do that. So let's go back here and let's create a different one. So not calls obj, but then let's call this calls. Let's see which of these have a lot of unique values. Okay. So if you wanted to find the number of unique values, so so let's say pandas number of unique values in a column. What is that? It's okay to use the dot n unique function. So I'm going to put that filter here. Okay, I'm going to put that filter here, and I'm going to say, you know what? Okay, yeah, give me this, but in addition to this, it should be object and x call and unique should be less than n. Okay. So if we were to take x dot n unique, you see how many, there's a very high number of unique values. Even if you look at suburb has 314 unique values. We don't want numbers 0 to 313 in there and then all of them be used, right? So we only want things like, so let's look at this. So type has 3, so that's a good one. You know, method has 5, that might be a good one if it wasn't dropped. So so if we go back here and we say, all right, I want to also look for only the ones that have, you know, less than 10 unique values. And I'm going to now call this calls cat, because now these make sense to be categorical ones, right? Okay, so that only brought type, method, and region name, right? So we basically went down here. We had a bunch here, but the small number of unique values is what made it to this. Those are those 3 columns, okay? And now we want to do this with calls cat, right? And okay, so it's pre-processed them now. And now let's run our function again and see if we could get a better result. The best one we got so far was 166. So let's go ahead and call this. Okay, and then but this time we're going to call it XLE. This is label encoded train. And this is label encoded test. Y train and Y test. Right? Let's see what we're missing here. Oh, XLE train, XLE test. Oh, I guess it wasn't stored outside, so let's go ahead and here, no, same error. So let me see what we're missing here. Oh, it's because we didn't filter the columns here, right? We should have filtered the columns here because it's still trying to use all the columns. So let's say calls okay, and then let's do add it here. So we still want to filter those columns. There you go. So we got an error. Oh boy, that error is a lot worse than it was before, right? Well, now we're only using 3 columns, but what if we want to use all the good numeric columns that we got here, right? We had calls num. So let's go ahead and add the numeric columns as well. So we have the categoric columns, and then let's also add the numeric columns. This basically is going to give us hopefully the best of all the columns that we have created so far. Okay, so this might take a few seconds here, combining. Awesome. So we've got an error now of 156,000 compared to with the numeric features, we got it down to 166. Right, it was the best we had. So by adding the categorical columns, we have now brought the error all the way down to 156. Okay, so we are not yet done for the day. We want to improve this further, and for that, I'm going to quickly go over one of the alternate models that we want to use. So just give me a second here for me to bring that up. Okay, so one of the models that we want to talk about is so we've done random forest, and random forest is better than decision trees. We talked about that last time. The reason random forest is better than decision trees is because we're not just going with the one tree, right? We're going with many trees, and then there's an element of randomness that's added. But the question is, can we do better? So in random forest, what we were doing was, so we would create one tree based on the whole bootstrapping and bagging, if you remember. Yeah, we have that right here. Yep. So we did the bootstrapping up here, and then we created all of these trees, right? But the interesting thing is that each tree is independent of each other. Okay, so here, so you might have this, you might have this, you might have something else going on. So you have, these are all sort of taken independent of each other, and then they are bagged together eventually to get your result. But then the question comes up is, the fact that they're completely independent means that over time, you're not really, as you move through this process, you're not really learning anything, right? You're basically just repeating the same process over and over. So the question comes up is it possible that we can learn something along the way? And so in order to, get better at creating trees over time, we go back to another idea, okay? And here's what we're going to try to do, okay? So let's see. So if we were to, let's take an example. And again, these examples are not mine. These are borrowed from Josh Stamner. It's some very good videos, and I'll again share the links with you down below. But let's say that we have a data set, and we have a prediction, okay, of some sort. Let's again, house price. Let's say we're trying to predict house prices, and then we have the number of say bedrooms, the number of bathrooms, the car spots, right, or the size. All right. So, what if we start with a very sort of dumb estimate? Okay? We take the average home price, and then we take that as, all right. So say my average home price is, I've taken the average of this entire column, which is my target column, and my average home price is somewhere in the let's say it's $702,000. Okay. So if I take that, and then I have each of my prices here, right? So suppose my first price was actually $880, and the next one was say $760 or something. Then now that I have this average estimate, what I do is I go and calculate the difference. Okay, so I'm gonna come up with a column now that calculates the difference. Let's do that down here. So I add a column that says this is my, I'll call it residual, okay? So this is, so for the first, I'm going to take 880 minus 712 because my dumb estimate is 712. I'm seeing how bad was I, right? So, you know, I'm 168,000 off, okay? And this is my residual column that I've added. And so if I know that, if I know what my residual is, then I can take, I can say that my prediction, let me write that here, my prediction is that I take my average weight, which is 712, right? I take 712. Let me write it out here. Prediction is I take 712 and then I add my residual value, right? Coming from 168 here, right? And which will give me my prediction of 880. So I took my simple prediction and I added my residual to get my actual. Well, that's fine. And I would have done that for the 760 also. And then, so it would take, the residual here, the residual value, and I would add that, and that would give me the prediction for the second home here. But that basically, I'm taking all of my residual, right? But that might get me to my exact prediction, but I might be overfitting by trying to take the entire residual into account. So what I would do is I'm going to add, just put a value between 0 and 1 here, and I'm only going to take a portion of it. So let's say I'm going to take 0.1 times that, okay? And I'm going to do that for all of them. So I'm going to say plus 0.1 times everything, right? So this is my, what we call it, the learning factor, okay? So I want to take a portion of my error, and then I'm going to now, as a result of that, I'm only going to take 0.1 of that, which would be, 16.8. And so this value will be 712 plus 0.1 times 168, and then my new residual, right? My new residual here, so this is in iteration 1. So now I have my residual with iteration 2. So this gives me a value of, so 712, and then 10% of that, and I take 880 minus that, which is the actual, right? Which gives me a new residual of 151. Okay, and let's do that here. So 712 plus 0.1 times 168 gives me 728.8. Okay, and then I'm going to take 880 minus that, right, which gives me 151.2. Okay, so 880 minus 728.8 is 151.2. So we can rewrite this now. We can rewrite this whole piece as, this is 712 plus 0.1 times the previous residual, which was 168, and then I'm going to take 880 minus that, right? And that's what gives me this value, 151.2. So now you see that this residual here is lower than this one here, right? So now you see that this residual is going down, right? It's decreasing residual. And we have a way to calculate what my residual is, right? So you see that if you keep doing this, then your residual is going to keep decreasing and decreasing and decreasing. And what is actually happening is, if we go back here, what is actually happening is that we are, instead of not learning like we did in the random forest, we're actually starting with something very simple, right? Which is a dumb estimate, if you want to call it that. And then we are sequentially, right? So then we say plus, and then we say 0.1 or some learning factor times a mini decision tree. Okay, but this decision tree is predicting the residual, not predicting the actual target. Okay, so let me go over that again. Where did we get? So we knew that our residuals here in iteration 1, we got this just by taking 880 minus the average. And then at this stage, right, we build a decision tree to predict the residual value of 168 and all of these values, right? That's how we got a decision tree at this stage, which is this one. Okay, so we built a decision tree, and using that decision tree, but we only applied a small learning factor to it. Remember, the reason we would pick a decision tree is because we can calculate the residuals, but we are not going to have it for all of them, right? We have our training and our test set, right? So in order to predict the residuals for the test set, we build this decision tree. Okay? And then we do the same thing here. We build another decision tree here. So what we're essentially doing is we start with our simple estimate of the average, and then we know our residuals. We feed those residuals in and build a prediction model for the residuals, but then we only take a small portion of that. Okay, and then as a next step, and then we add to that again. Now we got our new residuals, and then we built another prediction model to predict the residuals, and we take a small portion of that, and then we just keep going on and on and on until either the residuals are very small, or adding another decision tree doesn't help anymore. Okay, so by doing this, essentially, think of somebody playing golf, for example. Whenever somebody plays golf, you have them start at the team position, and then let's say this is where they start, and then they're trying to get it right. The first shot gets it to a certain point, and then the next shot, maybe they get it to this point. Let's say this is where the flag is, and then the third time they overshoot it, right? So this was the first time, iteration 1. This was iteration 2. Then iteration 3 got them here. So you see that they're always trying to minimize that error from what they should be, right? And then maybe from here they tried to hit it in, and then they got to this point, and then eventually they get there, right? So this method that we just talked about typically, in some cases, does better than random forest, because we are learning along the way, right? Along the way, and the method of learning, because we are predicting residuals, and because we are only taking a portion of it, this is called, so gradient descent is where we use a gradient to keep trying to go closer and closer. But then here, what we are also doing is, because we're building these little trees, this is called gradient boosted trees. Okay, so that's what this is called. And so I'm gonna add a link to sort of an actual small example of this, and you can kind of follow through with it. But hopefully, it makes sense that we are, by predicting the residuals, we're trying to get closer and closer to the error over time. So that's the fundamental difference: is we are predicting residuals here and not the target, right? But by taking portions of that residual, we are sort of coming closer and closer to where we want to be. All right. So there are still, it doesn't mean that random forest is always better than gradient boosted trees. For example, whenever you have data sets with a lot of noise, if you have data sets with a lot of noise, then random forest is better, right? Because it can, the noise gets sort of randomly divided up, right? So this is good for here. So this is good for, all right. This is, random forest is good for noise. Whereas if you have less noise, then gradient boosted trees are better. But gradient boosted trees also do well for whenever the data is unbalanced. Okay, so anytime you have unbalanced data sets, then gradient boosted trees do good. So, having said that, let's go back to the code and see if we can, in the next 10 minutes, quickly build a gradient boosted model. And gradient boosted, here we're doing gradient boosted regression. Right? So let's go into, say, let's see, Python. Boosting regressor. So sklearn has one, but what I would suggest is there's another one. Let's see. XGBoost here, right? XGBoost happens to be one that is very strong and very has performed very well. So I would suggest just look for XGBoost, which stands for extreme gradient boosting. Example. The nice thing is that even whenever people go ahead and build, create new libraries like XGBoost, they still follow the basic, define, fit, predict type of structure. So go down here and see, all right, where do we get XGBoost from? Let's see here, they're loading the data. Right, so it's a new library. It's not from sklearn. It's called XGBoost, and then there are some libraries within that. We're going to use the regressor, and then we're also going to try to play around with some of these. So learning rate. Remember that learning rate we saw. So the smaller the learning rate, it's going to inch toward. It's going to take longer, but it's going to get better. Because it is taking smaller steps. It's not overshooting too much. Okay, and then you have the n estimators. That's another big one. That's how many of these trees you want to build. Remember, we said we would want to. The higher that is, typically it would help more. But again, it's a balance between low and high. When you're too small, you'll be underfitting. Too much, you'll be overfitting. You want to have it somewhere in between. And then max depth is each tree, each one of these small trees, how deep do you want to let it go? So those are the common parameters we might want to tweak. So let's go ahead and do that. Let's see, build gradient boosting model. And for this, I'm going to actually copy, in the interest of time here, I'm going to go ahead and copy the code. Again, the nice thing is it follows the same structure. And but we do need to bring in XGBoost. So it was import XGB, yeah, XGBoost, right? I already have XGBoost. You might need to install it, pip install it. So from XGBoost, and XGBoost is very big, by the way, in size. So I would think about that. Right, we have XGB regressor. That's what we're going to use, and then we are going to XGB regressor. Just have a seed in there. So instead of random forest, let's go with XGB now. And right. And here, instead of X train, let's go ahead and use the best data frame we have so far, with the best training set in the test set with the right columns. Let's use that here. And Y train is just Y train. And for our predicted value, let's use X test XLE with the label encoding. And right, so we've got Y test and Y test pred. So hopefully there's no typos in there. Oh, no. Yep, that would be good. Okay. Let's print out the. Okay, so this gradient boosting method gave us an error of 159 compared to 156 from before, right? Which we already got from random forest. So the question is, can we do better? Let's tweak some of the parameters and see if we can do better. So in here, we had an estimators, right? An estimators of, say, 3,000, and then we have our learning rate. All of these have default values, of course, right? So we're just seeing if we can do max depth. These are the three that we wanted to try. Max depth of, say, 5 nodes. That we got 159. Okay, previously, as the number of estimators increases, as this number increases, it takes some time because it's trying to run it. Oh, great! So you got the 151. So that's already better than this. And so now we can go ahead and write a function to kind of iterate through different values. By the way, there is another method called hyperparameter tuning, which is a big area in machine learning, which essentially gives us some libraries that can go and do the iteration for us. We can just give it lists of, hey, run through all of these values. So for example, if we go higher on this, then we might get something better. But then if it's too high, so we can give ranges of values for n estimators, a range of values for learning rate, ranges of values of max depth, and it would go and then come back with, okay, here's the best combination for you, right? So that area is called hyperparameter tuning. All right, so just adding more got us to 150, and so you can kind of keep it. So far this has been the best result we have got, the lowest error, which is a far improvement from the 238 that we started with. We've essentially brought in additional columns, numeric columns. We've taken our object columns, looked for the categorical columns, brought those in, and then we've applied gradient boosting to further improve it by learning better over time, and then as a result, we've come to this law set, right? So those are the takeaways from this class. So starting next week, we are going to kind of switch over to a different area. But let me go back here and go to our intro. I promised last time that we would keep building this, and at some point in time, I am going to try to put this in flow chart of some sort. But you guys should be creating this on your own. So we said yes, our target is continuous, and so that's why we're doing regression. We don't think there should be we don't know that there should be any relationship, which is why we came down to decision trees. Then we said we're going to combine decision trees using randomness, and then here we're saying we're going to combine trees. We're going to combine trees, using gradients, right? And so that is the gradient boosted trees. Okay, so this is. And if we had known that there was some sort of linear relationship, we could have gone down to linear regression, right? So that essentially takes us, completes our work in the regression space. There are many, many, many other algorithms in regression. There's types of regression even under linear. There's lasso regression, ridge regression. You guys can go look into those sometime. Those are just small changes to linear regression. But the nice thing about decision trees and random forest and gradient boosted is you can very well explain all of these models to somebody. You could have applied neural networks here as well. For regression also can be applied, but then that goes into not so easy to explain models, right? So we've taken up the whole time for today.